Hi everyone, my name is Brayden Schott from the University of Wisconsin-Madison, and today I will be sharing our work using information bottlenecks to enhance distance-based out-of-distribution detection. Now, out-of-distribution data is any sort of inference data with some feature deviation from a model's trained feature distribution. This sort of data poses a risk to clinical deployments of models because model output on OoD data is generally untrustworthy. To mitigate this risk, it is recommended to implement out-of-distribution detection algorithms. One such family of algorithms is referred to as distance-based algorithm, where some distance measure between the distribution of features found in a model's trained data to a set of features found in an inference data sample is measured, and higher distances are generally associated with higher likelihood of that inference data sample being out of distribution. One limitation of this approach, however, is that it measures all features equally when it is known that not all features are equally important to the prediction task. This brings us to the purpose of this work, which is to enhance distance-based out-of-distribution detection via feature importance weighting, which is now indicated in the figure to the right here. Now, in order to determine individual features' levels of importance to the prediction task, we implemented information bottleneck optimization. Now, if you consider a neural network as some information system, the goal of this process is to statistically minimize the amount of information at some point in this network. This is accomplished through a post hoc loss function, which consists of the model's standard loss, and some loss function, which describes the amount of information in a system. Intrinsically, this removes unnecessary information from the system. So we implemented this on a unit model designed for segmentation, where after each model encoder layer, we placed an information bottleneck block. Within each of these blocks was the only learnable parameter in the model at this time called alpha. Now this alpha parameter determined how much each individual feature was either preserved or replaced with noise via this interpolation function defined as z. Now this noise replacement strategy is how information is minimized in our system. Because of this, the information loss was approximated as the KL divergence between the z variable and some prior distribution q. And this information loss is computed for each encoder layer. So information losses across layers were individually weighted and summed to a single global information loss where the weights were predefined. Importantly to remember from this slide, however, is that the learned alpha parameter here is what determines feature importance. Using this learned alpha parameter, we defined our weighted OoD distance measure as the average deviation of test sample features from the trained feature distribution weighted by this alpha parameter. This was computed for each encoder layer, so this measure from each encoder layer was weighted and summed across layers to define our global weighted OoD distance measure. This was compared to its non-weighted counterpart distance measure and also to the Mahalanobis distance of bottleneck features. This work was built upon a segmentation model trained to segment liver organ and liver lesions, and this model was trained using 104 publicly available CT images. And this training data is what defined our in-distribution data. Now, the test images were defined using 31 internally available CTs of patients with metastatic neuroendocrine tumors, and this test data, or some perturbation of this test data, was used to define our out-of-distribution data. In our first assessment, we looked at the correlation between each OoD distance measure and lesion segmentation performance. Here in this plot, we're showing the Spearman correlation coefficient for this assessment across distance measures, where in particular for the weighted measure, we're showing the trend of this coefficient as a function of information bottleneck optimization iterations. And from this trend, we see that this weighted measure achieves stronger and stronger correlations across optimization iterations. And this is especially apparent when we look at the scatter plot between these two variables, where the distribution between these two variables gets more and more correlated across iterations. Comparing to the comparison OoD distance measures, we see that this weighted measure is really necessary to attain a strong correlation in this assessment. For the second assessment, we looked at each OoD distance measure's ability to detect perturbed image data. For this, we applied the fast gradient sign attack on our test data at 5 unique perturbation magnitudes, and this constructed 5 different OoD test sets ranging from near to far OoD types of data. And now the task of each OoD distance measure was to distinguish this type of data from the model's trained data. Doing so and looking at these trends of the area under the ROC curves for this task across distance measures and across perturbation magnitudes, we see that the weighted measure did achieve superior detection of this type of OoD data, especially at smaller perturbation magnitudes, which may be more indicative of the types of shifts that we can expect in a clinical setting. So in conclusion, we found that feature importance weighting in the context of distance-based out-of-distribution detection algorithms both enhance the correlations with segmentation performance as well as enhance detection of perturbed data. Future work entails the implementation of this methodology on different types of OoD data, as well as assessing its effect on clinical endpoints. With that, I'd like to say thank you for your attention and thank you to the University of Wisconsin-Madison for supporting this work. Bye-bye.